So as we have planned before, we want to bound this probability by here. For that, we need to show that for module tree, this is bounded by PT. And for weak module tree, we have additional term. So this is true. Now we want to bound this by some number here. And for this, we want to use the structure of weak module tree. And this weak module tree was defined in this way, which makes which kind of gives you a recursive structure. So it's easier to bound the summation of P, which can be proved in this lemma. Suppose that there exists some number x alpha, which is bigger than or equal to p alpha for each alpha in I, and which also satisfy this relation. Then the expected length of log is at most summation of x alpha. So if we prove this, then we can actually show that this modulus fixed algorithm can produce a good randomized algorithm for many applications of local lemma. So, as we discussed in here, we only have to bound this quantity, the summation of all PT for module tree T, and it can be upper bounded by summation of PT for all wing module tree. And let WD alpha as a T wing module tree with root label alpha and depth MOST. For that, we add all the P of T. So from this, we want to use the recursive structure of wing module tree. If you have wing module tree with alpha as a root, then all the children must be labeled with labels which is related to alpha. And each of them is also wing module tree. So this is wing module tree, wing module tree, wing module tree, and each of them has depth at most d-1. So as every wing module tree with root labeled alpha decompose into the root and some weak module tree with roots beta. Hence, we have the following recursion. So you take the root, which gives us this number P alpha, and we consider all the beta, and we take the 1 plus t minus 1 comma beta. So here we consider 1 plus t minus 1, say beta prime, beta, say beta 1, t minus 1, beta 2, 1 plus w of t minus 1, beta 3, and so on. If you multiply this with this, then you get the model tree, which looks like beta 1, beta 2, beta 3. If you multiply this, and this, then you can consider all wing model tree, which has a root with alpha, labeled alpha, and then its children have a label beta 1 and beta 2. And this, multiply this with this case, is alpha and just beta 1. So that's why we add 1 to here, so that any combination, if you multiply these, you get the 8 terms, these 3, this, and this, and this, and this, and this. So there are 8 possible combinations, which give you all possible rooted tree with these structures on the top, and then rest of them are included inside of here. So that gives us this recursion. Now we claim that this is at most x alpha for all alpha inside of I by induction on D. So if D is 0, then we have that depth 0 tree is just one vertex, which is root itself. So in that case, you just multiply p alpha, which is at most x alpha, from our definition here. Our condition on the lemma. So base case is okay. And suppose wt minus 1 beta is smaller than x beta for all beta inside of I. Then by the recursion above, what do we know? We take all the beta which is related to alpha, and we multiply this number, and this is at most, by our induction, this is at most alpha of x of beta. One plus x of beta. But how large is this? Because of this assumption, we know that that's at most x of alpha. So induction holds. If it holds for d minus 1, it also holds t. So we prove this claim. So using that, if you take the summation of t being module 3, then that's basically, that's same as the summation of all alpha. You consider the limit when t go to the infinity, w of t alpha. So by our definition, so if t goes to infinity, then that you consider the all possible wing module tree with root alpha, and then root could be one of the indices in I, and that's at most, I mean, each of these is at most xi alpha, so its limit is also at most x alpha. So this proves the lemma. So now we consider the local lemma application. In the local lemma, what we do is we often consider some xi in this dependency diagram. This holds, so that's our assumption in local lemma. Then what we do is we let x of I, so this I plays the role of alpha here, x of I be xi for all index I. Then what do we know? Probability of this ith event happen is same as pi, and j is in the out neighborhood of the dependency diagram is same as I and j are related in the above setup. So these are the in an application of local lemma. Then we have this x of alpha is at least p of alpha times so this is the relation we get. So we take this and then we divide it on this side, then this is what we get. And because this x of beta that we take, which is xi, is at most 1, so this is actually lower bounded by this, which satisfies the condition here. That means as long as local lemma works, the previous lemma implied that modulus fixed algorithm has expected length of the log and most summation of xi. In most of the applications of local lemma, there are polynomially many bad events, and each xi is polynomially small. So this expectation is at most some polynomial. In most of application of local lemma, I and xi are polynomial, so this I is size of I is only polynomial. So expected length of log is polynomial, say big O of n to the s. Then by using Markov, what do we know? The algorithm ends in, say, this time, with probability at least 1 minus some big O of n to the minus s prime. So, and with similarly in the symmetric case, we can even show that, symmetric case with the dependency digraph having that degree m of d, we can even show that expected length of the log is m of the size of I divided by d. So this concludes the section of local lemma, section 5, and then next time we will move to section, in next video we will move to section 6.